All right, I think we're good to go. Um, so a lot of stuff to do today. We're definitely picking up the pace today. So this is going to cover a lot of material. Um, I'll be posting the lecture as usual, unless I have technical difficulties, right? Um, but definitely ask questions as we go because we're going to go through a lot of new stuff today. This is really sort of the jumping off point where we get into, pretty much all stuff that is new compared to what we do in 120. Let me start off with just a few comments on Lab 1 though before we jump into materials. So first of all, I was really happy with people's Lab 1 reports. This is far better than I ever get on Lab 1 or even Lab 7 as far as completeness and quality and legibility and people, including all the things that are supposed to be included. So the reports that I got, they looked like, technical reports. They were full lab reports, descriptions of experiments, all that stuff. Really good work. So I left feedback. I left voice feedback, which hopefully worked. Again, I was having some technical issues, but if I left you a voice note with nothing in it, let me know. But couple of general comments. So one, I want to see an introduction to the lab. So before experiment 1, just put in 1 or 2 sentences and say, in this lab, and then talk about, basically what the lab itself is about, and then starting with experiment 1, experiment 2, and so on and so forth. Make sure you describe procedures. So if you say something like, I built a circuit and measured the output, and it was 5 volts, right? Well, what circuit did you build? Put in a picture of the circuit. How did you measure the output? Where did you measure the output, right? So the protoboard connectivity, I used a multimeter to find connectivity in the protoboard. Here's what it looked like. Well, how did you use the multimeter? What was your procedure, right? And keep in mind this idea, somebody else, on the other side of the planet can pick up your report and do the same steps that you did and see if they get the same result. That's basically what you do publications, reports, things like that for. So make sure that somebody reading this knows what steps you did so that they could do the same steps. Experiment 4 saw a lot of confusion there about truth tables. And this was the main point where people lost points on the lab. So let's look at the truth table for Lab 1, Experiment 4, because this is going to be something you use for the rest of the quarter mostly. So west, east, south. And so start with a system diagram, inputs and outputs. And again, I want 6 outputs. Okay, so I want red and green lights for each direction. So let's do green west, green south, green east, red west, red south, red east. On your report, hopefully your arrows actually line up with your labels, but I'm new to this. So 3 inputs, 6 outputs. Okay, so let's look at what the truth table would look like. So make sure that if you have a truth table with 3 inputs, you have 2 to the third or 8 output rows. And I had a number of reports that only had 6 or 7 output rows. So there's 8 outputs. And let's do a sidebar here about counting in binary. So we'll come back to the lab report in a second, but I'll write this pattern about 1 million times in the next 8.5 weeks, right? And so this is, how we count in binary. So if you're not sure how to do that, let me show you a technique that works for this. So if you only had 1 bit and you wanted to count in binary, well, you'd go 0, 1, right? That's pretty much kind of your only choice, except maybe 1, 0. So if this is how we count in 1-bit binary, if we want to do 2 bits, what do? Just repeat this pattern. So now you've got 2 copies of this. On the first copy, put a 0. On the second copy, put a 1. That's how we count with 2-bit binary. If you want to count with 3-bit binary, repeat this whole pattern. So now we've got 2 copies of this. In the first copy, put a 0 in the beginning. Second copy, put a 1 in the beginning. And you can keep doing this till the cows come home, right? You can go up to 4 bits, 5 bits, however many bits. To add one more bit, basically make another copy of, your n-bit counting sequence. Put zeros in front of the first half, ones in front of the second half. That gives you your n+1 counting sequence. And eventually this becomes second nature, but until then, you can use this technique, right, to go from 1 to 2 to 3 bits, or however many bits you need. And technically, your truth table is correct if these rows are swapped around, but anybody in the world that you try to show a truth table to, they're going to be expecting your bits to be in this order. Most anybody. So it's good to know how to do that. All right, so what do our outputs look like? Green west, green south, green east, red west, red south, red east. So the deal is, east is the highest priority lane. So if there's a car on east, it should get to go. So anywhere I have a 1 in my eastern input, I'm going to match that in my output. And if east has a green light, then none of the other lanes should have a green light. So that takes care of the case where there's a car on the east. If there's not a car on the east, but there's a car to the south, for example, right here, then south should get a green light. Also down here in the 7th row, there's a car to the south, but nothing to the east. So in those cases, south gets green, everybody else is red. And then there's 2 cases left. West has a car and nobody else does. Definitely west should get to go there. This first case where there's no cars anywhere, you can either make all the lights red or you can pick one light to be green. And it's going to simplify your logic a little if you made this as a 1 and a 0 and a 0. But technically anything in there would be correct. Alright, and then the red lights are just the opposite of the greens. So we can think of the logic in terms of the greens, and then we can just fill in the reds to be the opposite. And when you build your when you design and build your circuit, you'll probably just take the greens and run them through inverters for your final circuit. But we'll do some.
I did green west.
Cool.
On the last one.
Mm-hmm.
Oh, your last. You accidentally did green west as 1.
You are right.
Yeah.
Thank you.
Yep.
You just saved some really bad collisions in the intersection. All right, so that's a good truth table for the traffic intersection. If you don't understand this, or if there was some confusion, let me know, right? Because I saw a number of truth tables that all looked like each other, but were not doing the same thing. For example, a number of reports had west looking like it got priority, except when there was a car on the south, and then the south got priority instead of west, and that didn't really, I couldn't see an interpretation of this that would explain that truth table. So if you don't understand this, or you understand this differently, right, come by office hours, lab hours, let's talk about it and figure it out, because it might be something weird about how the lab is written up or something. But that's a good truth table. So other comments on the lab in general. I saw a bunch of very good new experiments, right? So that was really good. Make sure that when you come up with a new experiment, you write it up like an experiment. So let's look at lab 2, for example. So lab 2, experiment 4, right? Use this chip as U2 and build a circuit shown below in Tinkercad. Use the Tinkercad to implement the above circuit and create a truth table by setting switches to all their possible positions. Confirm that the performance is consistent. If you read this description, it's fairly clear what you're supposed to do for this experiment. Now compare that to a situation where it says, experiment 4, play around with some other chips and see what they do, right? That's not very specific. And the results of that experiment, how is somebody else going to compare what they did, right? What does play around with? What chips are they going to do? What are they going to analyze in their performance? So you want enough detail that if you saw that experiment in a lab, you would have no doubt about what it is you're supposed to do. So be very specific, and then, and this is really important, do that experiment and write it up and put it in your lab report as a new experiment. So for example, in lab 1 there were 4 experiments. This is experiment 5. And you're writing it up and you're reporting on it and you're putting in your observations and conclusions and all that. The only difference is you're coming up with experiment 5, but then you're doing it and you're including the write-up in the lab report. Right? So the new experiment is a really significant chunk. It's another experiment to do, but it's also one you have to come up with, and you have to design, and you have to write the description of it, and then you have to do it. All right, and most of these things, the not having an intro, not having, not doing the new experiment, I didn't take off points for lab 1. Okay, I will for lab 2 and going forward. All right, so question in chat, what's the parentheses around the 1 here? What I meant here is you can put anything you want in here. You can have all the lights green, all the lights red, or you can have one light green. So if I just had south or east being green, or if I had them all red, that would be fine. So you don't have to have a 1 here for this truth table to be correct. These other values, these are really the only values you can have and have your truth table be correct. But you have some choices that you can make for this first row. I think the easiest choice to work with is to give west a green light in this case as well as that case. So that's why I put it in parentheses, because that's not the only valid truth table.
I have a question.
Yeah.
With regards to the new experiment, when you're coming up with the new experiment, I read on the guide to writing lab reports that you didn't need to write a whole write-up of the new experiment, just like presenting your expected results. On lab 2, do you still want us to write like the full procedure and observation and stuff for our own experiment?
Yeah, I want you to do it like another experiment. I should update that guide to writing lab reports, because that sounds like it's not accurate anymore.
Okay.
Let me see what I did in here. Formatting organization, final conclusions, new experiment, think of a new experiment, extend it further, think deeper, then write an experiment with sufficient detail, a few guidelines, include enough detail. Okay, so yeah, I say in the write-up you do not have to perform the experiment yourself. That is no longer correct. So I will change that and I will repost that after class. Thanks for catching that and asking about it. And again, I didn't take off points for lab 1 for that. All right, any other questions or comments?
I had one about question 9 on the homework from yesterday.
Okay. And I only had one person come by lab hours and ask about the homework, which I was kind of surprised, because question 9 we did not have a chance to talk about in class, and it's in the book. But yeah, let's talk about analog to digital converters. So the basic idea here is imagine that you so we have some questions where it says, if you have this many objects to categorize, how many bits do you need? or if you have this many bits, how many objects can you categorize? And it's this notion of, you know, n bits gives you 2 to the n buckets, right? So if you have 2 bits, you have 4 things that you can code, and you can use the bit pattern 0, 0, 0, 1, 1, 0, 1, 1. So if you had 4 states your system could be in A, B, C, D, you could say this is A, B, C, and D. If you needed to store information about, you know, one of 5 things, 2 bits is not enough. You'd have to go up to 3 bits. Okay, so that was some of the earlier questions, like question 7, right, about works of art in an art gallery. Okay, so this is very similar. What's going on here is we're taking an analog voltage. So let's say we have a voltage between 0 and 5 volts. And this voltage could be, you know, all kinds of weird shapes. But we know the lowest it gets is 0 and the highest it gets is 5. And we want to store information about the value of this signal across time in binary. We want to code it as a set of 1s and 0s. So if we have, for example, 2 bits available to do this coding, we can break this voltage range into 4 buckets. And so we can split it at 1 volt, 2 volts, 1.25, 2.5, 3.75, and 5. And what we would do is we would say, you know, anything from 0 to 1.25, we'll code that as a 0, 0. And from 1 1/4 to 2 1/2, we'll code that as a 0, 1, and so on. Alright, so we're basically assigning a bit pattern to each of these ranges of voltages. Alright, and I'll draw one up here. So suppose that we have, you know, this signal that's moving around, it's changing smoothly, right? And we decide to encode it with this binary coding, right? What happens is between here and here, all we're going to do is we're going to say, you know, the voltage between here and here was 0, 0. That's all we can do. We can't record the fact that, you know, right here it was lower than it was right here, and right here was the highest that it was, because we don't have enough bits. All we can do is say between here and here, it was somewhere between 0 and 1 1/4, which is what our code 0, 0 means. And then we could say over here, the voltage level corresponded to 0, 1. And then from there all the way over to here, all we can do is say 1, 0, somewhere between 2 1/2 and 3.75. So this is an approximation. And sometimes the approximation is good enough, sometimes it's not. For example, you know, our waveform rose up and then it dropped down and it rose up again. We've lost that information. All we know is that between here and here, it was somewhere in that voltage range, 2 1/2 to 3.75. Whereas over here, we happen to luck out. And we know that right here, it was between 1 1/4 and 2 1/2, so that's a 0, 1. But then right here, we know it was below 1 1/4, so that's a 0, 0. And then right here, it went back up. And so sometimes, you know, if the signal changes a lot, we can record a lot of information using just these 4 bits. But sometimes not, right? Like between here and here. So in general, if you have a certain range of voltages that you're converting to digital, and you have a certain number of bits, you can ask questions like, what's the finest resolution that we can discriminate in our input signal? And in this case, the resolution would be 1 1/4. So 1.25 volts. And all that means is that, it's possible for our voltage to change by, 1 1/4 volts, and we don't know it. In other words, from here it went from 2.5 to almost up to 3.75, but we just recorded it all as being, voltage level 10. So resolution is how fine a change in your input will register as a change in your coding of that input signal. And so the book develops some formulas for this, and in Engineering 270 we dig into this a little further. But basically the idea is if you have n bits, you have 2 to the n, I'll just call them buckets, categories, containers, whatever, right? N bits let us code 2 to the n different pieces of information. And whatever your maximum and minimum voltages are, so let's call it Vmax and Vmin, the difference between those, that's the total range of voltage that you need to encode. So if you do Vmax minus Vmin, that's our 5 volts in this case. And if you divide it by the number of things that you're going to split that range into, that gives you your resolution. So that's the basic formula we use when we deal with something like A to D conversion. The voltage range divided by the number of buckets gives you the resolution. And so the questions in question 9 are different variations on this. So part A says, what's the resolution? Let's see. Determine how many output bits are required. So we're trying to find n. Okay, in part A it says the resolution should be less than or equal to 4 millivolts, and the voltage range is 24 volts. So part A is telling us Vmax minus Vmin is 24 volts, and our resolution should be less than or equal to 4 millivolts, so 0.004 volts, and we want to find n. So resolution of least significant bit, that basically says, if we change 1 bit, the rightmost bit, we want that to correspond to, a change of 0.004 volts or better. So we want to find an n, so you basically plug in 24 over 2 to the n equals 0.004, and flip it around, 24 over 0.004 equals 2 to the n. Find what this number is, and now you're back to, one of those earlier questions about works of art and trying to store them using bits. So 24 over 004 is 6,000. So you're looking for an n where 2 to the n is at least 6,000. And the closest power of 2 that's bigger than 6,000 is 8,192, which should be 2 to the 13th. And so you need at least 13 bits. Now what happens if you have more than 13 bits? If you've got, 100 bits of coding, then your resolution is going to be 24 over 2 to the 100th. It's going to be a really, really, really small number, nanoamps, right? And if you can resolve, or nanovolts, if you can resolve a nanovolt, right, you can certainly resolve a change of 4 millivolts. So more bits gives you a higher resolution. If you only had 12 bits, right, that's 4,096. And so 24 divided by 4,096, that's about 6 millivolts. So it's not quite enough resolution.
It's weird I got it right, but for the wrong reasons.
Really?
Yeah, because I went with basic math, so I turned to find n, I went and found, log 2, 6, 7.
That's exactly the right way to do it.
And then I was like, okay, and then I need to be able to round this up to a specific bit, so it's within this measure, so 13 bits.
Yeah, no, that's perfect. That's the more precise way to do this. So if you know that 6,000 is 2 to the n, and you're okay with logs, the log base 2 of 6,000 equals the log base 2 of 2 to the n, which is just n. So you're really just asking what's the log base 2 of 6,000. And you can do that by taking log base anything of 6,000 over the log base the same thing of 2. And so that should give you 12 point something. And then question B and C are just different. B says the range is 25 volts, resolution is 1 millivolt, so same formula. And then C says the range goes from negative 20 to 30, which means, you know, the voltage range is 50. And a unique output every 15 millivolts, that's just a different way of saying you want a resolution of 15 millivolts. So that if your input changes by 15 millivolts, you get a different output. So you can resolve that small of a change. Alright, and that's not the question I'm grading for the homework, so.
Oh, really?
Yeah.
I got it completely wrong.
Oh, that's okay. Yeah, that's I'm not grading that one because we didn't go over that, and it's not the central theme of chapter 1. So I'm actually grading question 6.
So to be,
To B?
yeah.
Let's see. So 25. So 25,000. So I'm gonna guess that's probably 2 to the 15th, 32768. So I think 15 bits would do it.
Yeah, that's what I got.
Okay,
Hey.
cool. And then for C, 50 over 0.015, so 4,096, 2 to the 12th. So 12
so
bits.
You weren't supposed to add 1 to the resolutions, as in, like, instead of 25 divided by 0.1 milliamps, or 1 milliamps, it would be 1.1 milliamps?
I don't think there's a reason to add 1.
Okay. Oops.
Adding 1 was in the equation, though.
Well, so if you're, are you looking at the book or are you looking at the solutions?
I was looking at the example problem.
Yeah, so stay away from those, right? Not that there's anything wrong with those, but reverse engineering a solution and then forward engineering it to your solution is probably not going to help you understand it as well. But let me see what the text does. So this +1 over here, there should be some parentheses here. It's really saying, you know, let's take this and divide by the resolution, and 2 to the n has to be bigger than or equal to that +1. I think that's just trying to deal with the rounding business.
Oh, so it's like adding an extra bit at the very end.
It's adding an extra 1 at the very end. It's saying if you wanted, yeah. And it shouldn't change your answer, but if you do the resolution +1, then you're going to get a totally different answer.
I think I had started doing it with the resolution +1 and then realized that it's
Okay.
not where it's at. So
You would
Yeah,
add the
yeah.
1 for extra accuracy, right? At the very end?
I'm not 100% convinced yet that it actually belongs
I
there.
don't know that it needs, yeah.
Yeah.
But
Because
it's
the number is so large, you don't necessarily just need that extra 1.
right. Yeah, it's probably not going to change unless you're right on the boundary. So if you had 5 volts and you wanted a resolution of 1 1/4, 5 divided 1 1/4 would be 3. Sorry, it would be 4. I think n equals 2 would get you there. So, and I think this is, might not be entirely correct. But it shouldn't end up changing your answer in most cases, unless you're really on an edge case. Maybe. Yeah. Don't do the +1. That's the easiest answer. But if you do, definitely don't, you know, add it to that. Add it to this instead. And I think by adding +1 guarantees that any change in that resolution will change the bit pattern. All right, cool. Other questions? All right, so let's go back to looking at going from a truth table to an equation. So remember, our goal for this first part of the course is to pin down this design sequence from some problem to a system diagram to a truth table to equations to a logic diagram to a wiring diagram to final circuit. A physical circuit, except our physical circuits aren't physical because they're done in Tinkercad, but you know, the actual final working thing. So problem is, you know, design a traffic light controller, blah, blah, blah. System diagram is the box that says what are the inputs, what are the outputs, what do the ones and zeros mean. Truth table describes how the outputs relate to the inputs. Okay, that's what you did in lab 1. Equations say, you know, what are the Boolean expressions in terms of the inputs that will generate the correct outputs. Logic diagram is the thing where we have the OR gates and the AND gates and wires connecting them and so on and so forth. Wiring diagram is where we actually have particular parts, not just an AND gate symbol, but we say this is a 74 LSOH, and pin 7 goes to ground and 14 goes to power, and this input goes to pin 1, and the output comes from pin 3. That's the actual thing that we would use to put wires into a protoboard to build our circuit, and then the final circuit is, you know, the thing that we actually hook up to a power supply, and we flip the switches and the lights come on, and all of that. So that's the first part of the course that we're in right now, is sort of exploring this pathway. And you know, problem statement is usually what you're starting with. System diagram, you draw from that. And truth table, you have to, you know, basically analyze what the problem's supposed to do, fill in the ones and zeros. Okay, so the next big part is going from the truth table to the equations. And really, once we have equations, going from there to a logic diagram, very straightforward. That's this mechanical procedure that we went through quickly last week. And then from there to a wiring diagram, that's picking parts out of your parts container, and, you know, this should have, you know, power on this pin, and this input goes here, and so on. And then this is, you know, plugging the wires into holes on the board, or dragging and dropping in Tinkercad. So this is where most of the work comes. And we've got a number of things we can do to go from a truth table to equations. So we're going to start off by reviewing this idea of sum of products. Okay, a sum of products is, you know, something like this, right? Where each of these is a product term. That's an AND of some things. That's an AND of some things. That's an AND of some things. So those are 3 products, and then we sum them together. We OR them. Okay, so this is a sum of products expression. And, you know, it might be X equals all of that stuff. So we know how to do this in some ways from past work. So let me make some truth tables. And the basic setup is you know, you got some ones and a zeros. So we have this sum of products approach where we basically do the following. We look for each row where there's a 1 in our output. And we write a product term corresponding to that. And a rule we can use for writing the product term in a given row is we look at the inputs. And if the input in that row is a 0, we write that input variable with a bar on top. If the input is a 1, we write that variable without a bar on top. So this row corresponds to A bar B C, and this row corresponds to A B C bar. And if those are the only rows where x should be a 1, then we can immediately write x is just the sum or the OR of those expressions. So that's a perfectly valid sum of products representation of x based on this truth table.
We can simplify this too, right?
We can simplify it, and that's what we're going to spend most of the day doing. But how would you simplify it?
You would take terms that are in both expressions that are ORed together, and if they're both the same thing, then I think you can remove them.
Okay.
If one's yes and one's no, you can get rid of it. So A, it has both, you can get rid of it.
Yeah, so you might observe there's a BC bar and a BC bar in both of these. And so we could do some factoring. Like that. Because A bar B C bar, that's the first term, and A B C bar, that's the second term. And then we could look at one of our identities and say, you know, A bar ORed with A, that's always true. In other words, is A true or is not A true? Yeah, one of those is guaranteed to be true. So this is actually like 1 ANDed with BC bar. And 1 ANDed with blah is just blah, right? If this happens to be true, 1 and true will be true. If this happens to be 0, 1 and 0 will be 0. So this is exactly the same thing as BC bar. So if you're savvy with Boolean algebra, you can observe things like this and do a simplification. And this is, you know, an easier circuit to build than that, because this needs 3 input AND gate, 3 input AND gate, and an OR gate. This just needs a 2 input AND gate, plus some inverters. All right. So simplification will be an important part of coming up with the equations that we're going to use to actually make a logic diagram. But we're going to learn a very systematic way to do the simplification that doesn't require any algebra. All right, so we'll come back to that in a few minutes. So here's a sum of products, and what I mentioned last week is that every time that we write a sum of products, it's always, you know, a bunch of AND terms. That's a recycling truck. They'll leave in a minute. It's always a bunch of AND terms ORed together. And regardless of, you know, what my output values are, yeah, I'm closing the window. It's not significantly quieter, but it's a little. So this first row, right, if we use this trick for writing, you know, A's, B's, and C's with bars on top, if we had a 1 in this row, this would be the expression A bar, B bar, C bar. This would be A bar, B bar, C. This would be A bar, B, C, and so on. And you get really good at writing these. And you get so good at writing them that eventually you realize, hey, I don't actually have to write these. I'm just going to call this, you know, expression 0, 1, 2, 3, 4, 5, 6, 7. And when I say, you know, expression 6, I mean A, B, C bar. And so we come up with these abbreviations that we call min terms. And it's just a lowercase m with a subscript. Now, if all I have is M6, how do I know that it's ABC bar as opposed to CBA bar? You need to know what order these inputs are in. And so you'll see something like, you know, X of ABC, and we'll list the inputs as if this was a function, right? So X of ABC equals, and now we could just write minterm 2 ORed with minterm 6. And that gives you all the information that this gives you. The ABC tells us, you know, if we put ABC in this order, then we want a 1 when minterm 2 is a 1, is active, or when minterm 6 matches the inputs. And if you think about the binary, this 2 down here really tells me the values of A, B, C should look like the binary number 2, 0, 1, 0. And this 6 down here tells me that when the binary number corresponding to ABC looks like 6, 1, 1, 0, we want an output of 1. So if I have an n down here, when I look in the nth row, my output function should be 1. And in the nth row, if I look at my inputs, they should look like the binary version of n. So you'll notice that as you're going through the homework, you'll see that pattern. You can use that pattern so you don't have to actually write out, you know, 64 rows. If you have a function with 6 inputs, you can start to find some shortcuts. All right, so those are minterms, and then the other thing was, you know, this is an explicit representation. We can also represent this implicitly, like this. So we use a summation to say we're just adding up some terms, and in this case we're just adding up terms 2 and 6. So this also captures all of the information in this truth table. And there's homework questions that will work on that as well. All right, note for later.
I have a question.
Yeah.
I'm noting a slight pattern with the 0 placement in minterms.
Mm-hmm.
Because in programming, you always start with the placement 0.
Mm-hmm.
Is this why it starts with 0 because of the relationship between the two?
That's one of the reasons, yeah. It's an interesting question why in programming we always start from 0, like with arrays and stuff. It just makes things work. and you know, in here it's exactly what you're observing. If I started with minterm 1, well, that's not what 1 looks like in binary, right? And if this was minterm 2, well, that's not what 2 looks like in binary. So yeah, it keeps these things lined up with their binary representation. All right, so hold this in mind. I want to talk about simplification, and we're going to use something called K-maps. And we'll see, you know, systematic ways to simplify truth tables like this. When we're done with that, which will be later on today, we're going to come back to this and we're going to do a dual version of this called a product of sums. And it's going to be exactly the same thing, but kind of in a parallel universe version. So like Evil Spock universe version of sum of products. But it will probably feel totally different, right? But it's really just going to be the same thing. So we'll come back to this in a few minutes. But let's talk about simplification of equations. And so this is going to be using a method called K-maps or Carnot maps. And let me try to give you a motivation for this. All right, suppose this is our truth table. And we can write down, you know, the sum of products expression. So this is A bar, B bar, C, and this is A bar, B, C bar, and this is A, B, C bar, and this is A, B, C. And down here at the bottom, these bottom two rows, we can make this observation immediately that someone made earlier with our other truth table, which is these two expressions are almost exactly the same. In fact, they only differ in this last term. And if we just think about the truth table, forget the equations, what's happening in these bottom two rows is in both cases A is a 1. And in both cases B is a 1. And in this case C is a 0, C is a 1. But in both cases X should be a 1. So just looking at the inputs and knowing that in both of these rows we want the output to be a 1, what we can say is we need A and B to both be 1s, but you know, it doesn't matter what C is. C could be a 0, C could be a 1, makes no difference. And so we can write a different kind of term here, which is just AB. And if A is 1 and B is 1, we know the output's a 1. Doesn't matter if we're in this row or that row, because both of those rows have a 1. Everybody see that? So this works really well visually because these rows are adjacent to each other. We saw two rows right next to each other with a 1 in each row, and you know, that jumps out at us. And we can actually use something called the adjacency theorem, which says the following. So this is the adjacency theorem. XY or XY bar is the same thing as just X. And it's really speaking to the fact that, you know, if these rows are adjacent to each other in a truth table and they have the same value, we can throw away that one variable that's changing. But it's not so clear in a truth table like this that we have the same situation, because this one and this one are not next to each other, but they could be. If we had written our variables in a slightly different order, these two ones would have been next to each other. So if I had put A over here and then B and then C, these ones would be just like this. So if we could look at our truth table and sort of in our minds rearrange the variables in all possible ways and look for things where there's two ones right next to each other like this, we could simplify. Now these two ones doesn't work, because actually we have two variables that change from one row to another. So we can't just look for two ones next to each other. But if we had, you know, a 1 right here, we could do a simplification on those two. So that's all preamble to a technique called K-maps. And K-maps are a way to visually redraw our truth table that will make these kinds of opportunities jump out at us. Okay? And this is going to look a little weird maybe. We're going to deal with 4 inputs. That's the most we can easily do with a K-map. And 4 inputs is certainly more than we can usually do comfortably just by looking at a truth table. So let's look at functions of 4 inputs. I told you you get really good at writing this after a while, right? All right. So let's just imagine a truth table. All right. Now we could start writing down a sum of products expression, but what's going to happen if we do that? We have 1, 2, 3, 4, 5, 6, 7, 8 ones. We're going to end up with 8 product terms being ORed together. That's an 8 input OR gate, and 8 4 input AND gates, and a bunch of inverters. Okay, that's a lot of hardware. That's, you know, a few protoboards worth of logic. It's lots of potential for wiring errors. It's lots of vulnerability when it's in operation, and so on and so forth. So we would like to come up with a simplified equation for X. So here's how we do a K-map. First we draw a 4x4 box. And we're going to put 2 variables on each side. And I'm pretty much always going to do A, B over here, and C, D going across. This part is really critical. I'm going to number the sides, but I'm not going to number them in the usual binary way. I'm going to number them in this funny way, 0, 0, 0, 1, and then I'm going to do 1, 1, and then 1, 0. And that's super duper critical. If you don't do that, the whole thing breaks. So 0, 0, 0, 1, 1, 1, 1, 0.
Just because you want to like group all the ones together like you did at the top there.
We want to group all the ones together.
Okay.
All right, so let's start a procedure. So step 1, make a grid. Label sides carefully. 2, we're going to fill in the ones. Okay, so what does this mean? My first one is when A and B are 0 and C and D are 1, 0. So there's one box here where A, B is 0 and C and D are 1, 0. That's right here. I'm going to put a 1 in there. I also want AB is 0, 1, CD is 0, 0. That's this box right here. 0, 1, 0, 1, that's this box. And 0, 1, 1, 0, that's that box. 1, 0, 0, 1, so 1, 0, and 0, 1. And then 1, 1, 0, 0, 1, 1, 0, 1, and this last row is 1, 1, 1, 1. That's this box right here. All right. Any question about how I put those ones in?
So you're just looking at the cases for when the first 2 digits are 1 and 1, and like you're looking at the first 2 digits and the second 2 digits, and you're putting it in the position.
Exactly. Yeah.
Okay.
So this one corresponded to A and B are a 1, 0, which is, you know, everything in this row. And C and D are 0, 1, which is everything in this column. So this box right here, A and B are 1, 0, and C and D are 0, 1. So that corresponds to that row of the truth
So
table.
it's like a Punnett square.
Yeah, yeah.
Okay.
All right. So I've got my K maps. Fill in the ones. And we haven't talked about don't cares, but we will. Eventually we'll have truth tables where there's some rows where we may not care if it's a 1 or a 0. And so we want to fill in the ones. We also want to fill in the don't cares. All right, that actually makes life easier. We'll come back and talk about those later. All right, so fill in the ones. Okay, our next step is doing what we call cover the ones. And we're going to cover with rectangles. And we have some rules. So we're going to draw rectangles around the ones. But we have some rules. So rectangle side has to be either 1, 2, or 4 in length. We can't have rectangles with a length of 3 or a height of 3. So we can draw a 1 by 1, a 2 by 4, a 1 by 4, and so on, but we can't draw like a 2 by 3. So rectangles have to have sides that are a power of 2. Don't cover zeros. So I'm not allowed to draw a rectangle that includes a spot that doesn't have a 1 in it, or a don't care. It's okay to cover a 1 more than once, but we need to cover each one at least once. When we talk about don't cares, you can cover those or you can leave them uncovered. Why? Because we don't care about them. And then the general rule, larger rectangles are better. And fewer rectangles are better. Alright, so we're going to try to draw rectangles around the ones. And make sure they have lengths and heights of 1, 2, or 4. We can cover ones more than once. We cannot cover the zeros, and we have to cover all the ones. So for example, I can draw a rectangle right here, and I can cover 2 of those ones. That's a good rectangle. So what are some other rectangles I could draw here to cover up the ones?
You could get from 0, 1, 0, 0
Mm-hmm.
to 1, 1, 0, 1.
Yeah, so there's a nice 2 by 2. I could do this with 2 2 by 1 rectangles, but bigger rectangles are better. So that's great. That chews up 4 of my ones. That's a good coverage.
And 1, 1, 0, 1, and 1, 0, 0, 1.
Yep. So let's pick up these two. And I only need to cover 1 once. So, you know, I could pick up just this spot right here. But again, bigger rectangle is better.
And then basically just the...
And then same thing here. Yep.
Would it be a problem to just have a 1 by 1?
So you can do a 1 by 1, but a 2 by 1 is larger. Larger is better.
Okay.
Okay, and we'll see why that is in a second. Alright, so we cover our ones. And then we write a product term for each rectangle. And this is probably the most error-prone spot of the process. So let's pick out this big rectangle here, this 2 by 2 rectangle. And what we want to do is we want to look at how the variables A, B, C, and D, what their values are in this rectangle, which is actually a square. So the variable A, for example, on these two values, A is a 0. On these two values, A is a 1. All right, here it's a 0, here it's a 1. So whether A is a 0 or a 1, we can still be inside this rectangle. So A doesn't matter. The variable B at all 4 values is equal to 1. So B has to be a 1. What about the variable C? What does it look like at all the spots in that square?
Zero.
Yeah, here, 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 and here, we're in this column or this column, C is always a 0. And D, what about D?
Always, no. Doesn't matter.
Doesn't matter, because, you know, these spots D is a 0, these spots D is a 1. So D doesn't matter. Alright, so the variables that don't matter, we're not going to worry about them. But we want B to be a 1 and C to be a 0. So we want to write an expression which will be true when B is 1 and C is 0. And that's just B ANDed with C bar. So same thing we were doing over here. If this variable has to be a 1, we'll write down the variable. If it has to be a 0, we'll write the variable with a bar on top. So that's how we write a product term for each of these rectangles. So this rectangle here looks like A has to be a 1. It looks like B could be a 1 or a 0, so we don't care about that. Looks like C is a 0 and D is a 1. And so this is the expression A, C bar D. And this rectangle here looks like A is a 1, B is a 1, sorry, A is a 1, B is a 1, C could be a 0 or a 1, so we don't care, and D is a 1. So that's the expression A, B, D. And last rectangle of the bunch looks like A is a 0, B can be a 0 or a 1, so we don't care. C is a 1, D is a 0, so this is A bar, C, D bar. And then once you've got those product terms, just sum those. And that'll give you your final expression. So in this case, X would be BC bar, or AC bar D, or ABD, or A bar CD bar. There's your final answer.
I'm actually having a hard time with why is it because it's one over the other that it doesn't matter?
It's because so let's look at this upper rectangle here, right? So clearly C has got to be 1, right? And clearly D has got to be 0. If D is 1, we could be, in one of these, but not there. But the variable B, right? If B is a 0, then we could be in this upper spot. If B is a 1, we could be in this lower spot. But assuming that A is 0, so we're in one of these two rows, and assuming that C is 1 and D is 0, so we're in this column, right? We know that we're either in this box or this box, depending on the value of B. Well, if B is a 0, we're in this box and we want our output to be a 1. If B is a 1, we're in this box and we still want our output to be a 1. So whether B is a 0 or a 1 doesn't change the output value. So that's the sense in which we don't care about the value of B, right? It doesn't matter. And this is really just, picking up this adjacency from the truth table. We're looking at
And my understanding is that because the numbers overlap at some point, same Z's just don't matter.
yeah, so we're really looking at these two rows in the truth table, right? Where A is a 0, C is a 1, D is a 0, and in this case B is a 0, in this case B is a 1. But both of those rows we want the output to be the same. So it doesn't matter if B is a 0 or a 1. As long as A is 0 and C is 1 and D is 0, we know the output should be 1.
You mentioned before we did this that the biggest you could do this for was like a 4-input equation, right?
Mm-hmm.
So, if we need to, could we always do this with Boolean algebra if, say, the inputs get bigger than 4, or is there another trick like this we can also do?
So there's a
curiosity.
there's a few options. So yeah, you can always do simplifications with Boolean algebra. It's just trickier when you have 6 or 7 variables to keep straight, all the ways that you can factor things and so on. But there's a technique called systematic algebraic reduction, SAR, which I don't actually talk about, but the book talks about it, that you can use to kind of methodically work through the equations and do the simplifications. You can do a three-dimensional K-map and get up to 6 variables. And if you're good at drawing hypercubes, you can go up to any number of variables that you want, but you might need a 4 or 5-dimensional piece of paper. But computers are really good at this. And so in practice, you know, we rarely do this ourselves. We mostly get, you know, a computer program to do it for us. But we're doing this, you know, for our simpler circuits that have, you know, 3 or 4 variables, and also just to kind of understand the mechanics of what's going on.
That'd be a cool coding project.
It is, yeah, totally. And it would be cool to do some visualizations of it in 3D also. All right, so there's a simplified equation from our truth table using a K-map. That's pretty much the whole procedure. There's one other thing I didn't tell you yet, but I'll tell you shortly. But let's erase this and let's do one more example, and then we'll take a few minutes break, and then we'll go on to product of sums. I'm going to do an imperfect erasing job here. And assuming that you know how to go from the truth table to the K-map, let me start just with the K-map itself instead of the truth table and going from the truth table to the K-map. So let's just start simplifying some K-maps. So here's a map with some ones in it. And, you know, we could do a rectangle here. That's pretty clear. We could do a rectangle here. And with the rules that I gave you, we would have to do, you know, a little 1 by 1 and a 1 by 1. Okay, so there's an extra rule, which is edges wrap. So this is like playing asteroids, right? This bottom edge is connected to the top edge, which means we can actually do a 2 by 1 rectangle that looks like this. And that's going to be fewer rectangles. It's going to be a bigger rectangle. So your edges wrap on top and bottom. Your edges wrap on left and right. And so this rectangle...
Rules again, real quick.
Yeah. I may have these posted on Canvas. If not, I'll see if I have them written up and post them.
Thank you.
Mm-hmm. All right, so this 2 by 1 rectangle, right, A doesn't matter, B has to be a 1, C is a 0, D is a 1. And this rectangle here, A is a 0, B is a 1, and D is a 1. But this funny broken rectangle, right, A could be a 0 or a 1, so A doesn't matter. B has to be a 0 in both cases, and then C is a 1 and D is a 0. And so if we OR those together, that would give us our equation. And so the reason we want larger rectangles is because the larger the rectangle, the fewer the number of terms. Because the bigger the rectangle, the more likely a variable doesn't affect the output. And so we'll have more terms that don't matter and that we don't have to include in our expression. And so I'll show you the extreme of this wrapping. Right, we can cover this with a single rectangle, because we can make this funny broken rectangle that looks like this. And it's actually a 2 by 2 rectangle.
Wow.
And so A doesn't matter, B has to be a 0, C doesn't matter, and D has to be a 0. So just B bar, D bar. And this feels a little weird sometimes, this wrapping business, but one way to think about it is just imagine that you have multiple copies of this map. Right, so this would be 0, 0, 0, 1, and so on, and put another copy down here. And put another copy down here. And this would be 0, 0, and 0, 1, and so on. So 0, 0, 0, 0, well, that's also right here. Right, that's the same square as that. And 1, 0, 0, 0, that's the same square as that. And 0, 0, 1, 0, that's the same square as this. So if I drew multiple copies of my K-map, I'd immediately see I've got a nice little 2x2 rectangle right here. So that's the effect of doing the asteroids wrap around on the edges, is just having, you know, multiple copies of your truth table to help you see where there's adjacent ones that we can combine using the adjacency theorem. All right, and let me show you 3 pathologies and then we'll take a break. Okay, what if that is my K-map? In other words, I don't have any ones in there. I can't draw any rectangles, right? But this corresponds to a truth table where, you know, every output is a 0. So what's your equation? It's just x equals 0. I don't have anything ANDed together. Here's a really unpleasant K-map. So how would I cover this with rectangles?
You'd have to do 1x1s for each of them?
Yep. Only thing you can do here is 8 1x1s, and each of those is going to be a 4-input AND gate, and you're going to have to OR those together. This is the worst, one of the 2 worst possible truth tables to try to simplify with a K-map, because all you can do is 1x1 squares.
What's the other?
Just do a mirror image, so put the ones in all the spots that are open instead of the ones that I drew it in. It's the same situation.
Well, that doesn't even simplify at all.
That doesn't simplify at all.
Oh, well, I wouldn't consider it the worst. That means you don't have to do it.
Well, that's true. Worst in terms of what you have to do next, which is build the thing. But yeah, and very, very little work to do the K-map part. And so these correspond to exclusive OR and exclusive NOR functions, which we have other chips for, so we can do things with that. All right, now here's the happy day in 250 class. What if your K-map looks like that? How do you cover those ones?
The full 4x4?
Yeah, do a 4x4. That's good times. And so what's the equation for this? Well, if I write these out, you're going to find that, you know, A could be a 0 or a 1, B could be a 0 or a 1, C can be a 0 or a 1, D can be a 0 or a 1. None of the input variables matter. And the answer is x is just equal to 1. It's the truth table where every row has a 1 in the output. So those are sort of the pathological examples and the endpoint examples. All right, so let's take a 5-minute break, and we'll come back, and I will start talking about, well, I'll talk about don't cares, and then we'll talk about product of sums, and then we'll run through the homework 2 assignment really quickly. So we'll come back in about 5 minutes. All right, cool. Welcome back. So let me mention one more thing on K-maps. Interesting. Okay. So when we make a truth table, sometimes we have combinations of inputs where we don't really care what the output is. So for example, suppose this is our truth table, and we do K-maps with 3 inputs, and we just do a 2x4 or 4x2 instead of a 4x4. All right, so suppose we have 3 inputs to our circuit, and we want these output values, but suppose input A is only going to happen when B and C are also 1. A is going to be 1 only when B and C are both 1. So we never expect these input combinations. And since we don't expect those input combinations to appear, it doesn't matter to us what our circuit produces for those combinations. So we can mark those as don't cares, and that's what that dash means. And so let's make a K-map for this. And so I'll put A, B over here, and I'll put C there. And it's the same as with a 4x4. We just fill these in. We want to put in the ones. So A is 0, B is 0, and C is 1. That's right here. 0, 1, 0 is right here. And then 1, 1, 1 goes right here. All right. So when we fill in the ones, we also want to fill in the don't cares. And we just carry those over as dashes, like that. And then when we're in step 3 and we're covering the ones with rectangles, we're not allowed to cover the zeros. We have to cover all the ones. It's up to us whether we cover the don't cares or not. They're optional. So the way to think of it is, if covering a don't care will let me make a bigger rectangle, let's do it. If it would make a smaller rectangle, if I would end up with more rectangles, let's not do it. Right? So using this metric of larger rectangles are better, fewer rectangles are better. Using that metric, right, you can choose to cover or not cover the dashes. So in this case, right, how am I going to cover this one? Well, I could cover it, just with a 1x1, or I could cover it with a rectangle like that, or, I can cover the whole 2x2 with a big rectangle. And that's pretty nice. And this dash, I can actually use that to cover this little isolated one with a better rectangle. And this one up here, I could cover with a broken rectangle like that. And that's a really nice cover, right? This 2x2 is going to eliminate 2 variables from my product term, and these 2x1s will eliminate 1, so I'll end up with product term of 2 things, and then just a single term down here. And let's just look at this big square. A has to be a 1, B could be a 0 or a 1, and C could be a 0 or a 1. So this is just the term A. And that's what we know from our truth table, right? If A is 1, we're just going to set the output to 1. Because here we want it to be a 1, and here we don't care. All right, so there's a bunch of homework questions with K-maps to practice on these. Keep in mind that your solution may not be unique. There may be multiple ways to cover that are just as good as each other. For example, suppose I had a don't care here. I could cover this one by making a rectangle that includes this don't care, or I could cover this one by making a rectangle that includes this don't care. Makes no difference. They're both the same size rectangle. But I would not want to do both because I'd be doing more rectangles than I needed. Right? As long as I've got this one covered at least once, I'm good. If I do another rectangle, I'm covering it twice, which is needless, and I've got an extra rectangle. I've got more terms in my expression. But I could, cover it with just this instead of this split rectangle. That would be an equally good solution.
Would it be more efficient in that case to do a split square?
Actually, yeah. So in this case, the split square would be your best solution. You're right. Yeah, perfect. The other thing is, if there's a don't care that doesn't help you to cover it, just ignore it. It happened that, we covered all the dashes in here, but, there may be, an extra dash sitting somewhere that makes no, there's no benefit to covering it. Don't worry about it. All right. So that's a bit about K-maps. So let's go back to what we were doing earlier, this notion of a sum of product, and let's look at the dual of this. So this is called the product of sums representation. Give or take a typo. And let's go back to a truth table. And let's suppose our truth table looks like this. Now the way that we do this in 120, the way we did this last week and today, we basically said, let's look at all the places where our output is a 1. And let's write an expression which will be true for that combination of inputs. And then let's OR those expressions together. So that if you happen to be in this row, this term will be equal to 1. And when I OR it with the other terms, I'll be guaranteed to get a 1. But if I'm in this row, for example, right, none of the terms that I'm ORing together will be 1. This will be 0, this will be 0, and the OR will be 0. So my output will be the correct value of 0. Okay, we're going to flip that kind of in a weird, twisty-turny way now. And let's look at a totally different approach to writing an equation for a truth table. And I promise you, this is really the same thing, but I suspect it'll feel like something totally different. All right. So here's our approach. Let's think about the zeros, and let's write an expression that will be 0 in this case and in this case. So I want an expression which will be equal to 0 exactly when A is 0, B is 1, and C is 0. And will be 1 any other time. Alright, so I want an expression that's equal to 0. I'm going to write an OR expression. And my OR expression is going to be A, or not B, or not C. Now, first of all, if I happen to be in this row, A is a 0, so this will be a 0. B is a 1, so not B is 0. C is a 1, so not C is a 0. This is 0, ORed with 0, ORed with 0. Yeah, this will be equal to 0. But what happens if I'm in any other row? Well, if I'm in any of these rows, A is going to be 1, this whole thing is going to be 1.
Would you write the expression as not x equals these together?
You might do that, but I'm not going to do that. Because we're heading towards an expression for x, but that's pretty accurately a way to think about this. But I'm going to twist it at the end.
Is this De Morgan's?
This is deeply using De Morgan's theorem. Yes, absolutely. All right, so if I'm in any of these last four rows, I know this expression is going to be 1. And if I'm in any of these first two rows, b is a 0, not b will be a 1, this expression is going to be 1. And if I'm in this third row where c is a 0, c bar will be 1, this expression will be 1. So this term is going to be 1 everywhere except right here. And this is the dual to what we did when we wrote down a bar, b, c bar, and it together here. This expression is 0 everywhere except in this row. This expression is 1 everywhere except in this row. And I'm going to write a similar expression down here. I'm going to write a bar, or b, or c bar. And this is a 1 everywhere except in this row. And in this row it's a 0. And now I'm going to say x is the logical AND of these two expressions. And that turns out to be a perfect equation for this truth table. And the high-level view of it is, right, if I don't happen to be in one of these two rows, both of these are going to be equal to 1, and their AND is going to be a 1. And so x will be 1, which is what it should be if I'm not in any of those two rows. But if I'm in, say, this row right here, this expression will be a 0, and when I AND with anything, x will be a 0. And if I'm in this lower row, this second expression will be a 0, and whatever I AND with 0 gives me a 0, so x will still be a 0.
In this truth table, how would something like this transform into what is the term I'm looking for? A map for wiring.
So it depends on what equation you come up with. So I could write a sum of products, which would have, 6 product terms, all ORed together, so it would be inputs go into AND gates and those outputs go into ORs. Or I could wire it up from this equation, and this would be inputs going into a pair of OR gates, and then the outputs of the OR gates get ANDed. Does that make sense? And this truth table is fundamentally no different from this one. I mean, it looks peculiar because most of the outputs are 1s, but really it's just another truth table. And it's not going to affect, how we go from equation to logic diagram and so on. But because there's mostly 1s, it may end up taking less hardware if we do this product of sums equation.
Sorry for the background noise, but so this is basically just to make a smaller point when there's more ones than there are zeros.
Mm-hmm. Yep. Or, when you have a homework question saying do product of sums. And I don't think I've ever had a situation in my own life where I actually did a product of sums, other than, when it was a homework question or a test question when I was in school. This is not the way that I think about things. It's not the way that most people think about things. And I don't know why that is, but we tend to think of things in terms of, we see the things we want, and so what are the conditions for making that happen? And this is saying, what are the things that we don't want? Where don't we want the output to be a 1? Well, here and here, and so how do we make an expression that's not 1 in that case? But it's really the same thing. If we flip around 1s and 0s and ANDs and ORs, right, and we do the De Morgan magic wand, it's the same procedure. But, almost always we end up doing a sum of products. I don't know why.
So ultimately, if this was ever implemented into an actual circuit, or program for that matter, we just care about the two situations where it's not, and we convert them to be the truth, or they are the truth, right?
Yeah, yeah.
Okay.
So it really depends what your gig is, and like I say, in this course, you know, mostly we're doing homework questions and test questions. So you'll be given a truth table and told, you know, write a product of sums equation, and that's the main reason you're doing a product of sums in that case. And on the other end of things, right, in practice, this is done by computers. And in the end, you know, we pretty rarely actually put circuits together by hand anymore anyway. They're all done by computers and laid out using automated tools. So this is like learning assembly language. Not because you're going to do assembly language, but because, you know, this helps you understand C and Python and Java and so on. So this helps us understand how to use some of the automated tools that will do these layouts for us. All right, so the rule here is look where you have zeros in the outputs, write one of these sum terms, and then take the product of all of those. And so just like with sum of products, there's a sum term corresponding to each of these rows, and they look like this. And you can probably start to infer a general rule. Which is if you have a 1 for the input, write the variable with a bar. If you have a 0 for the input, write the variable without a bar. It's the opposite of what we did before. And we put plus signs in between these instead of putting in, you know, the implicit AND operation. We do ORs. And these things are called max terms. And we have abbreviations for them, which is an uppercase M, 0, 1, 2, 3, and so on. And so we could write X of A, B, C more succinctly as a product of what? This expression right here, which is M3, and this expression, which is M5.
Terms are looking for like the zeros, right?
Yep, max terms are written wherever the output should be a 0.
Okay.
And so we have a shorthand for this, which is to use a product rule and just list the index of the max terms that we care about. So product 3 comma 5, this means M3 ANDed with M5. So that's an uppercase pi instead of a sigma uppercase S, product versus sum. So the book goes through this in good detail, and there's a bunch of homework problems that we'll look at shortly that give you practice with this. So this is sum of product, or product of sums. And you can do K-maps on a product of sums. And how does a K-map work? Well, same basic setup. These things are all the same. But you write down your zeros. And you cover your zeros and your don't cares with rectangles. So maybe I'd pick up this one, and this one, and this one. And then you write a sum term for each of your rectangles. And so this rectangle right here, A has to be a 0, B we don't care, C has to be a 1, D has to be a 0. So the corresponding sum term for this would be A or C bar or D. Right? If the variable is a 0, we write it in its true form. If the variable is a 1, we write it with a bar on top. And so this rectangle, A doesn't matter, B has to be a 1, C has to be a 1, D has to be a 1. That's B bar or C bar or D bar. And this rectangle that's going horizontally looks like A is a 0, B is a 1, C doesn't matter, and D is a 1. And so that's A or B bar or D bar. And then your final expression would be the product of those. Give or take typos. There's your expression for X. And as you go through the homework, be looking for patterns, right? And you'll start to notice some things. For example, if I were to write this in compact minterm form, it would be the sum of all the minterms where x is equal to a 1. Well, that's minterms 0, 1, 2, not 3, 4, not 5, 6, and 7. So I can write my equation like this, or I can write my equation like that. Well, the terms that I put in my sum term were in my sum of products were exactly the terms I did not put in my product of sums. Right? This is everything except 3 and 5. This is everything except 0, 1, 2, 4, 6, and 7. And if I write down, the expression for max term I, it's the complement of the expression for minterm I. And you can verify that by using De Morgan's theorem. Right? Minterm 3 would be something like A bar B C. Max term 3 would be A or B bar or C bar. And if I complement this expression, I'll end up with exactly this, just by applying De Morgan's theorem. And if I complement this, I'll end up with exactly that. So there's all these symmetries in there, and you'll discover these as you're doing the homework by thinking about what you're doing and looking for patterns. So
you mentioned the book. Where in the book is this? What chapter?
Oh, I'm going to guess chapter 3, but that is purely a guess. Let me take a look at the book. Book. There's several versions of the book around, and I don't know if I have the latest, but the chapters haven't changed. So this is all chapter 2. So chapter 2 talks about K-maps and canonical or standard forms of functions. That will talk about both product of sums and sum of products.
Thank you.
Yep. All right, so let's take a look at the homework, and then we're done here for the week. So ignoring the S questions. Question 1: write the truth table for each of the following functions. So this is practicing interpreting Boolean expressions and writing truth tables. Right? This will have 16 rows. This will have 8 rows. This will have 4 rows. Okay, so write those out. Question 2, expand this function to its canonical or standard sum of products form. Easiest way to do this, turn this into a truth table and then write the sum of products from the truth table. Alright, question 3, expand this function to its canonical product of sums and sum of products. Again, 4 variables, write out the truth table. So going from an equation to a truth table, basically you've got 16 combinations of inputs for each of those. Figure out what this expression is equal to. And do it in parts, right? Make a column for A3, A2, make a column for A1 naught, make a column for A1 naught or A0, make a column for A3 naught, make a column for this column, ANDed with this column, and then make a column for whatever this column was, ORed with that column. That's your final value of F. But don't try to do it in your head. right? That's error prone usually. So break it into subproblems, right? Figure out what this expression is, figure out this expression and this, and then add those together and list that as another column, and then OR it with this to get the column for F. Once you have a truth table of ones and zeros, you can just write down the POS or SOP expressions really just from looking at it once you know the pattern of, you know, what do the min terms look like, what do the max terms look like. All right, question 4, compact min terms for each of these functions. So 3 input variables, here's the truth table. So here you want to write it down as just, min term 2 plus min term 4 plus min term 5. Okay, these equations up here, you want to, the canonical product of sums or sums of products, that's the big long algebraic expression, right? So A bar, B, C, or, M bar, R, S bar, ORed with, etc., etc. But question 4, write the compact expression. So just add the min terms. All right, question 5. Each of the following functions is written in form that's equivalent to the complement of the standard product of sums. In other words, this is the expression for F bar. So write the function F itself. Write each function in a standard product of sums and also in a standard sum of products. And you can do it in a compact form. So if F bar is equal to this, right, make a truth table for F, and then just write a sum of products and a product of sums for F in compact form. But look at the answers that you come up with and compare it to the original statement of this problem and see what you discover, right? Homework is all about learning. It's about discovery. It's not just about busy work. So writing the compact forms, when you're given an equation in this form, write an equation that describes the complement of F. This should be related to the solutions that you come up with. So think about that in addition to just...
What is the pi and summation at the front of the outputs for again?
So this is the product. So this says this is a sum of products, sum of min terms 0, 1, 2, 3, 10, 11, and so on. The summation says it's the sum. The pi is a product, so this is a product of sums, which means each of these is a max term. So this is the product of max terms 12, 13, 14, and 15. Product just meaning and sum meaning or. All right, 6, write the expression for each of the following in terms of the independent variables. So write expressions in terms of A, B, C, D, and E for this equation. So here you're being given the equation in min-term form and you're asked to write it out explicitly. And do this one first and think about it. You don't need to write 64 rows of a truth table to do this. You can get there that way, but there's easier ways to do it. And this is about discovering a connection between an expression in this form and an expression in, say, this form.
So you're wanting us to simplify?
Not so much simplify, but convert from this kind of expression to that kind of expression. A sum of products where you're actually listing, the individual inputs and their complemented values. But you can do that translation without having to go through a 64-row truth table in this case.
You can just find the binary number.
Yeah, basically.
And then that'll tell you what the input should be, right?
Right. But if that doesn't make sense to you, discover it. Don't try to get it from the solved solution. Do this, maybe come up with some of your own problems with 3 or 4 input variables, and do this translation from compact form to explicit form, and see what you discover, and you'll see some patterns. The remaining questions are mostly about K-maps. So 7, you're putting these functions on a K-map and then minimizing using what we did with K-maps by circling ones. Question 8, you've got a K-map and you've already got one circled, and you're supposed to write down the product terms corresponding to each of these rectangles, which are actually ovals or curves in some case. Question 9, I said to skip in the description on Canvas because we're not going to talk about prime implicants. So you can skip question 9. And then question 10, same thing, but use a K-map to find the product of sums, minimize expression. So cover the zeros. And then 11, one more question, and in the homework assignment I said you can skip doing the SAR approach, just use the K-map. And the MDs mean we don't care. So we care about min terms, 0 through 15, all of these should be 1s. Terms 9 and 11, we don't care, and then all the other terms are zeros. So put that into a K-map, cover the 1s, optionally cover the don't cares, come up with an expression. All right, and that's due a week from today, so you can work on it over the weekend. You can come to office hours, tomorrow or Monday morning, and then Tuesday there's also lab hours before class, and Wednesday lab hours before class. And we can definitely talk about homework questions in class on Tuesday. So if you've got questions that haven't been resolved by then, we can go through it then. Please don't put this off and start it, Tuesday night, because then, there's no real opportunity to talk about questions. And this homework can take a long time. There's a lot of writing, but it's time well spent. It will really help, cement some of these concepts, and there's a lot to discover in doing these questions. So if you can, plan to spend some time on this, right, rather than scheduling it at a spot where you can rush through it in a half hour or something, because it takes a long time. All right, we're a little bit past time. That's all I got for today. Have a good afternoon. I will see you next time.